Okay, so one more video for class 16. Here's another example. This comes out of Munson's book. And we have a certain spillway, we won't mention which one, for a dam is 20 meters wide and it's designed to carry 125 cubic meters per second at the flood stage. So we want to have a 1 to 15 model and constructed to study the flow characteristics of the spillway. And we want to determine the required model width and flow rate based on this, and what the operating time for the model that corresponds to a 24-hour period of the prototype. The effects of surface tension and viscosity are to be neglected. So, in looking at this problem, where we might start out is to do our Buckingham Pi thing and to find out all the dependencies that are involved here. And it's really sort of a flow rate thing is our primary look at. I didn't do the Buckingham Pi for this, and maybe I should have, but it wasn't done in the original book, so that's why I'm not doing it. But we do know that the surface tension don't matter and viscosity don't matter. So because of that, the Weber number doesn't matter, and because of this, the Reynolds number doesn't matter, right? So it's not dependent on those, so we're sitting there. But what we do know, this thing has a free surface, so the Froude number, which is defined as the velocity divided by the square root of gravity and the characteristic length, which we're going to assume is the width of this, those do come into play. So when we're talking about how to get to this right here, well, first off, they would say what operating conditions to determine the required model width and flow rate. Well, the width is pretty easy because they already said it was a 1 to 15 scale model, so that's like a little silly. So the width of the model is going to be equal to 1/15th of the real thing, which was 20 meters wide. So we're dealing with 1.333 meters. All right, so mission accomplished, kind of silly. That Froude number, what we could do is say the velocity square root of g over L of the model is going to be equal to the velocity square root of g over L of the real thing. That's supposed to be an L. It doesn't look like an L, it looks like an E. So, gravity is going to be the same onto this, gravity of the model on the real thing, because we're not going up to space. So we could say the velocity of the model divided by the velocity of the real thing is going to be equal to the square root of the scale, right there. Now, we could also use that we have the Q is going to be equal to the area times the velocity. And we don't quite know what area to do, but we do know that area is a length squared type of thing. So in terms of the proportions of it, the Q of the M could be equal to the velocity of the model times the area of the model divided by the velocity of the real thing divided by the area of the real thing. So we just established that this was going to be LM over L. So now we can go for the area of the thing. Well, let's just say that we know this can be proportioned, right? So, it might be the width times, let's say, the height, right? Because we're talking about a spillway right here. So we have like water spilling over there. So this is like the depth of this right there. We'll call that the height, and then the width of this. So if we're going to have a proportional area that we're doing with the thing, right, then that's what the 1 to 15 scale says that we have to. That means we're going to have, this is going to be length times length squared. So we're actually going to have the LM over L squared. So if this parameter right here, this we'll call it the length scale of the thing is L LM over L. What we're going to find with this treatment right here that we'd have a lambda to the 5/2, right? And so because you have this squared and this is to the 1/2, so we're going to add those together, we get to the 5/2. So what we could say is the Q of the model is going to be lambda of the L raised to the 5/2. And here's the flow rate of the real thing. So we're going to take 1/15 raised to the 5/2 and multiply it by 125. So now that the flow rate that we should expect, or we should be getting from our model, should be 0.143 cubic feet. Cubic feet should be meters, cubic meters per second. And by the way, we usually use the V with a cross through dot, but we're using a Q here. And an interesting extension on this is that they're going to say, what operating time should we correspond for 24 hours? So like how do we approach time? Remember, the velocity can be thought of as some type of length per time, right? So like if we were going to say that right here, we would say, okay, well then we have the velocity of the real thing divided by the velocity here of this. I almost kind of want to go the other way around. I'm gonna be okay. Sorry. We're gonna say, well, that's gonna be length over time times time over length of the model, right? Because this is the velocity of the model. It's on the denominator, so we have it like right there. We could combine these together and move these back over to the other side. I don't know. I'm trying to range for the for this, but we can have a time scale can be rearranged so that we have let's see if I'm doing this the right way. Yeah, so we're going to have V over Vm, and then we're going to have Lm over L. Did I do that right? I think so. Right? Lm over, yeah, good something. Yeah, yes. Which we notice is going to be 1 over the square root of our lambda L up above, right, because it's right there, times our lambda L, and that's going to be equal to the square root of the lambda L. So if we want to have the time for the model, we're going to have the square root times a real time, right? If we could follow that idea. So we're going to take the square root of our 1 to 15 times our 24 hours, and we're going to predict that we have 6.2 hours would be what we would expect for our model. So it's a interesting type of mindset into trying to thought process to try to run an experiment, to model something and to see what the parameters are, but you could kind of use a logic like that to arrange an experiment. And so that was the end of the example. I kind of liked that one, kind of interesting.